So what we'll do today is what we should have done yesterday, but we're going to take a step back, and instead of adding on to our Euler-Lagrange code, we're going to take a little bit of a, let ourselves be sidetracked a bit, and look at what an Eulerian-based code would look like. So what we've done so far, in any case, we're already solving the fluid equations in the Eulerian framework. That's not going to change. But we're going to care less about this, the coupling. We're just going to look at some of the very basic properties of Lagrangian versus Eulerian methods from the perspective of solving for the characteristics of the particle phase. In terms of content, and in fact it's pretty good because I might, in terms of content, there's not too much we're going to do. Essentially, we'll, for the first hour or so, we'll derive the required equations. Are you guys ready, or should I wait a bit? Yeah? In the first hour or so, we'll derive the Eulerian equations. We'll obtain what's probably the most naive Eulerian model for the evolution of the particle phase. And then I'm not going to be very, I guess I'm going to be a little bit dishonest in the fact that I'm going to take this very poor Eulerian model and I'll try to convince you that Eulerian models are not as good as Lagrangian models. So we're going to compare probably the worst of the Eulerian models to a decent Lagrangian model. At least I'll try to make the point that Eulerian modeling of particles is a challenge for a number of reasons, and I'll try to highlight very specifically one reason. So the plan is we'll talk about the underlying equations. We'll derive them in a way that's fairly appropriate instead of just postulating that the particles behave as a fluid. We will instead derive these equations in a way that's fairly reasonable. Then the second thing we'll do is, once we've obtained a very simple Eulerian model for the particle phase, we'll go back to what we talked about this morning a bit. We concluded with a discussion of preferential concentration, which showed that what we argued, or the way we discussed preferential concentration in a fairly hand-wavy way this morning, will just show that you can derive this process analytically, especially by just linearizing the equations. So that's going to be the first hour. Then we'll create a simple, extremely simple Lagrangian-based case that will run. We'll make some predictions as to what should be happening for that case, and you'll see that things will work fine. And then we'll generate the code that will allow us to do the same thing in the Eulerian framework, and we'll see where things fall apart. Okay, any questions before we start? Any problem, apart from the white spot that you guys have in front of you? No? Okay. So in your in the course spec that you have, you should have a chapter 5 document, and then you should have a Journal of Computational Physics article. We're going to talk about some portions of this chapter 5, which is a little bit longer. We're going to focus on one specific methodology. We're not going to talk in details about the paper, but I wanted to provide you access with this because it is directly relevant to how we're going to conclude this chapter 5. All right, so now we're back. We have, so in this chapter 5, I'm giving you a reference to a fairly recent 2012 annual review of fluid mechanics by Professor Rodney Fox from Iowa State University. He's probably one of the most well-known person in this very specific topic of Eulerian modeling for particle-laden flows. So he has recently written this review paper that essentially gives a high-level summary of the various techniques and the various ways one can think about modeling particle-laden flows from a Eulerian standpoint. So we've talked about Euler-Lagrange already. We'll talk more about Euler-Lagrange tomorrow. We'll derive a pretty comprehensive set of equations that would work for a full four-way coupled problem. Now we'll talk about Euler-Euler. So Euler-Euler is the approach wherein we're going to use a Eulerian description for the particle phase as well. We're essentially going to skip those concepts, but this is a nomenclature introduced by Professor Fox in this 2012 paper, wherein there's basically a way of distinguishing between different classes of Eulerian models for particles. One extreme case being the so-called macroscopic modeling approach. This macroscopic modeling approach would be typically what you would use if you were to use an Euler-Euler model in the context of a commercial software like Fluent. So if you're interested in doing Reynolds-Savage Navier-Stokes with particles for a full fluidized bed reactor or full gasifier, you're probably doing something like microscopic modeling. The idea here is that once you're at the macroscopic model level, you need to model the interaction between the two phases and the fluctuations that are inherent to the fact that you have particles in your system. Right? Remember, we've thought about the particles as a statistical problem. Basically, you have a distribution of velocities and positions for your particles. So at a given point, you can find particles going in different directions. So you have a certain probability density function of finding particles going from left to right or right to left. So if you want to close that and average all this, you're going to have fluctuations to account for. That's one thing that you're going to have to account for. The second thing is going to be the fact that if you're averaging either ensemble averaging or volume averaging a flow that is unsteady, chaotic, turbulent, you're going to have to account for fluctuations of the turbulent nature. The combination of those two things is what takes you to the macroscopic type of model. The microscopic model is the way that Professor Fox referred to particle resolved direct numerical simulation. Essentially a situation wherein you know everything. You're solving the equations in a pointwise sense. There's no averaging being done. You solve it for the surface of the particle. We're going to be talking quite a bit about this intermediate stage here. So I'm not going to tell you anything more at this point about how one would do a Reynolds-Savage Navier-Stokes solution of a particle-laden flow. This is too many steps of modeling removed from our level of discussion at this point. We're going to leave that to more applied engineers. This is too expensive for most purposes. We're going to find this intermediate ground as being very useful. So this mesoscopic model is going to be the following idea. Well, it's probably the simplest way of thinking about mesoscopic modeling is first Euler-Lagrange modeling is a good example of mesoscopic modeling. You've boiled down the entire interaction between the fluid and the particle in the form of a single drag force. Okay, now your particle that was a complex object that could potentially deform, that could have a flow inside, that could have lots and lots of additional complications. Now there's a position and a velocity, and the other thing that you care about is the rate of momentum exchange between the phases. Okay, that's what we talk about when we talk about mesoscopic modeling. Well, we're going to do the same thing for the in the context of Euler-Euler. So we're going to have a representation where we'll essentially look at particles as a collection of points that are assigned a velocity, and we're going to try to formulate our equations at that level. So I'm skipping the entire macroscopic discussion, and we'll directly jump to the mesoscopic discussion. So by mesoscopic, again, I mean we've given up on trying to resolve things at the level of the particle resolved direct numerical simulation. We essentially make the argument that this is too expensive, there's too much information, and it is too expensive. So we're going to boil that down to a simpler problem by essentially going to the question of a particle equals a position plus a velocity plus a drag model. That's essentially the main step we're going to do when we're going to go to the mesoscopic level of discussion. There's a pretty important aspect that I have here, which is that in the context of Eulerian methods, we're gonna think only about the level of a single particle. So I haven't introduced that yet, but we're gonna think about the prediction of a single particle. In a sense, we're not going to worry about making any prediction or formulating any equation for particle pairs or particle triplets. We're going to think only about what is the probability at one point, at one time, of finding one particle with a velocity of whatever and a diameter of whatever and a temperature of whatever. So we're not going to worry about two-point statistics. We're not going to worry about particle pairs. That's something, by the way, that a Lagrangian model would have inherently, because in a Lagrangian model, you know at all time and locations, if you're sitting in the position, if you have a particle sitting in a position, you can probe your simulation and figure out where are your neighbors, how far are they. We're going to get rid of that. We're not going to have access to this information with Eulerian representation. Okay, so now let's go through the mathematical formulation a little bit. So we're going to go essentially to the same approach as before. We're going to look at that from the perspective of probability density functions. The probability density function that we're going to be looking at, we're going to give it a specific name. We're going to call that a number density function, NDF. NDF is not a vague concept in the context of particle-laden flows. It's pretty specific, and it relates to the probability of finding a particle at the position x at the time t that has a velocity, say, u sub p. Okay, so now we're thinking about a probability of finding a particle with a given velocity. If you have a variable diameter for your particle suspension, then you would add naturally something like Vp, the volume of that particle, or we could have added instead the diameter of the particle. So this is going to be the joint probability distribution function of all the variables that are tied to the particle. So in the same way as this morning, we had this number density that was then multiplying a conditional probability of having a certain diameter. Now we're going to look at that, but from the perspective of velocity. So at a given point, I'm going to have an entire distribution of velocities that could be obtained by particles. So that acknowledges the fact that particles are not moving all in the same direction. At one given point, I could have two particles that are one going right to left, the other one going left to right. So I guess I should say it the other way, but you see what I'm saying. So this f sub p is going to be an important concept. Right away, we'll point out that this is not a particularly esoteric concept. As soon as you start extracting moments of that, it becomes very natural. First of all, the zeroth order moment of this thing. That takes us back simply to what we call this morning the number density. Okay, so my n of x and t is going to be the integral over all possible velocities, which should belong in R cubed entirely, all possible volumes, which should belong to well, the range 0 to plus infinity, of my number density function at x and t, which is a function of the statistical variables v sub p and u sub p that I integrate over vp and over up. Okay, so if I'm integrating over the distribution of velocities and distribution of or the range of velocities and range of diameters, I just get basically all the particles. I'm counting all the particles that are present at that location. That gives me back my number density. Now, if you're interested in the volume occupied by the particles, you're going to need to take a first order moment with respect to the volume. And that will take you back to volume fraction. So what we called alpha p earlier will be the integral over the full space of possible velocities, which is r cubed, and then all possible volumes going from 0 to plus infinity of the volume times the probability of having at that position at that time a particle of that volume and that velocity. Okay, so there's a connection between those very physical concepts we were talking about this morning and this maybe more esoteric statistical way of thinking about particles. We can continue. We can do first order moments in both volume and velocity. And what I'll get is the product between the velocity, the mean velocity of the particle, and the mean and the volume fraction of the particle. So I can extract from that the mean particle velocity. That's going to be alpha p times, let's call that big UP for the mean particle velocity, and that's going to be obtained again the same way. We're going to integrate over r cubed and over all possible volumes. So conceptually, this number density function is a very practical concept. Now the question is, we've introduced this concept. Okay, fine. We've shown that it's connected to the variables we were talking about this morning. Fine. So now we have this Eulerian high-dimensional quantity that we're arguing is a good description of our particle phase. Now we need a PDE that describes the evolution of that quantity. Well, that's not very complicated to derive, and in fact, the field that we're invoking here is in fact what's been called for many years physical gas dynamics. So we're going to essentially invoke kinetic theory. We're going to go back to the way people have gone from a molecular description of fluids to a continuum description of fluids. We're going to apply the same exact idea and apply that to particles. So essentially, we're going to make use of the so-called Boltzmann equation, but recast in the context of that number density function, but not applied to a collection of randomly moving molecules, but applied to a collection of randomly moving particles. So the first person to have done that is Williams, and that has led to the so-called Williams-Boltzmann equation that dates back over half a century now. And this equation might look complicated at first, but if you've been exposed to the Boltzmann equation, there's no surprise here. It's a pretty straightforward concept that can be derived without too much difficulty. So this is what the equation looks like. I should mention here that P here indicates the particle. But for the other indices, and I think there is only I, I'm using Einstein's notation. So I'll say here Einstein's notation used except for the P index. So we have a bunch of terms in this. What are those terms? Well, the most obvious one is the rate of change. So that's the temporal rate of change of our NDF. So what causes a change to the number density function? Well, let's look at each of these terms. This is the particle velocity dotted with the gradient of the NDF. This is literally a pure convection term. We're saying that essentially the NDF is being convected at the velocity of the particle. So I'll just write that in red. So this is a transport of particles in physical space, meaning in x, at velocity up. What is the second term? Well, the second term is now, it contains a derivative with respect to the volume. So that will describe the changes or the evolution of that function in volume space. So it will essentially tell us that particles are going to be moving from one volume Vp to another volume Vp at a rate that will be controlled by, say, an evaporation rate or a condensation rate or some sort of a growth rate that I wrote here as g as a function of all the other variables that characterizes the particles. So this is our transport of particles in Vp space. So the evolution, right? Remember, we wrote this number density function as a function of time, position, velocity, and volume. So it is expected that we should see transport in that in the volume direction as well. So this is due to volume change. And here I specified a rate of volume change that I wrote as just g. So that could be evaporation. The next term is the same story, but this time in velocity space. So now we are differentiating with respect to each component of UP. So now we're saying transports in the x velocity of the particle, the y velocity of the particle, and the z velocity of the particle. At what rate is this happening? Well, it is happening at a rate that's going to be controlled by the rate of velocity change. That will be literally the particle acceleration that we will express in the form of drag. So this is going to be the same thing, transport of particles in velocity space due to velocity change, therefore acceleration, due to applied forces. And here, specifically, we're going to be interested in drag. So we'll have one last term. This term will accommodate for changes in the NDF, both in terms of volume or in terms of particle velocity, due to particle-particle interactions. So this is essentially a collision term. This is saying that the NDF is allowed to interact with itself. If there's some physics happening at a given point between different types of particles, we can see a change. So for example, we could have here an agglomeration model. So we would have a certain probability at which particles present at the same location would merge together into one larger particle. So in pink here, this is the change. Due to particle-particle interactions. And here, typically that's going to be collisions. We're not going to worry about the details of most of this. The one thing that we'll care about is drag. So we're going to write what drag is for our problem. I wrote that as F in the general sense, but essentially it takes us back to our Lagrangian drag law. If we just stick to Stokes drag, if we forget about the little f as a function of Reynolds number, correlation coefficient, the drag ends up being difference between the velocity of the fluid and the velocity of the particle divided by the characteristic response time of the particle. If I multiply that by the mass of the particle, or the mass of the particle phase, I just get mass times acceleration. Therefore, this is my drag force on my particle phase. So this is naive. Again, you would want to have some sort of correction for higher Reynolds numbers. One thing that I should point out is you can also derive better correlations or other corrections for higher volume fractions as well. So if you have many particles, it is reasonable to expect a different drag. So people have over the years developed a number of models essentially from particle resolved simulations, so from microscopic scale simulations. They have worked out what the drag is, they've built correlations, and then they've re-injected that in those type of Eulerian models. I'll give you a couple of references, but there's a good number of them. There's been quite a bit of work. I've cited him already a number of times, but Shankar Subramaniam has a very nice correlation as a function of Reynolds number and particle volume fraction. And I think this is with a student called Tenetti. Another person who's done this type of work is Don Koch. Oops, it's not, it's an H. Who's done lattice-Boltzmann fully resolved simulations around particles and then extracted from that the drag and generated correlations to be then re-injected in the place of this F. Okay, so we're going to make our life simpler. We're going to assume that the diameter remains constant. It's given. Okay, so we're not going to worry about that. So we'll give ourselves the significantly simpler situation where G is equal to 0. The initial particle distribution is monodisperse, okay, single diameter. We're going to ignore collisions, and we can go back to that in a second. So we're going to say that there's no interaction between particles. So essentially I'm saying no evaporation, no collisions. Then if we go back up here, and if we trust our drag model, this is the evolution of the quantity we're solving for. This is that same quantity. This is the velocity. This is the statistical, the variable that corresponds to all our possibilities of velocities. This goes away. This here, we're assuming that we have a good drag law that's available to us, and that's equal to 0. Well, that equation is closed. There's, in fact, here, yeah, we're done. Everything works. So we could just solve that. So I want to point this out. That our equation 1 here is fully closed. Again, assuming our model for drag is a reasonable model that we trust. So that means that we could just solve this. And then we would be done. We would have the perfect Eulerian model. Why don't we do that? Right? Why wouldn't we solve this directly? How many variables do we have here? This f of p now depends on time, x, y, we've decided to ignore the volume. So it depends on the u velocity, the v velocity, and the w velocity. Okay, so now we're looking at a function that depends on 6 variables. Well, we know how to solve PDEs that depend on 1 variable, 2 variables, 3 variables, 4 variables. 4 variables, this is what we deal with typically when we deal with Navier-Stokes, right? Our velocity is a function of x, y, z, and t. Well, it gets to be pretty expensive. Now we're adding 3 more variables on which our function depends. That means that you would have to discretize space, time, x, y, and z velocity. All this you would have to mesh, and then you would have to solve the equations. The cost is enormous. This is not feasible. So it is closed, but it is unfortunately not good enough. So we could solve directly in principle. But fp is a function of x, y, z, t, up, vp, wp. So it's simply too expensive. So since we're not going to talk much more about collisions in the Eulerian sense, I will spend just some time now to talk about it, just to give you an idea how one would go about dealing with collisions. So there's one thing I told you a little bit before. If I scroll back up here, I underline this here. Closure occurs at the level of the one particle density function. What does it mean? It means that everything we're writing here for this NDF is the probability of finding. Oh, sorry, go ahead. I'm sorry, I can't hear you. So, okay, let me, can you say that again?
The gap closure model is probably valid for the dilute state. So that you have written there actually, it is only valid for a dilute region actually.
The drag law I wrote? Yeah, yes, so I agree. This is why I said right after that there's correlations that have been developed for denser regions.
So is there any universal model which could work for both denser and
Okay, so we'll talk about one tomorrow morning, but I didn't want to go beyond just this. So the answer is, are they a universal model? No. So the question was, if you have, this is for dilute flow, single particle essentially. If you have many particles, or if the Reynolds number is larger, this doesn't work anymore. So we talked already about the fact that you need to correct that to account for the higher Reynolds number. What's going to happen if you have a high concentration in particles is that you're going to need to have some sort of a different model. But we're talking here about the level of modeling. We're not talking about the real physics. So the people have the models, and this is why I gave those references here. Tenetti and Subramaniam have published one such model as a function of the local volume fraction as well as the particle Reynolds number. Don Koch and co-workers have done a number of models like that, and there's others. Probably one of the most well-known is one of the most used comes from Beetstra, who's done a similar type of correlations. So is there a universal answer? No. This is in fact a pretty challenging problem, but there's been a number of studies typically based on those type of micro-scale simulations that capture all the scales and all the physics from which you can explicitly measure what the drag is. And then people have correlated that to the volume fraction and to the Reynolds number in order to extract a single, fairly easy to use model to account for volume fraction. So this has been done by many, many different groups out there, and there's lots and lots of references. They tend to agree reasonably well with one another, which is kind of a relief. There's no single unifying theory behind this. There's one simple concept that we'll talk about a bit tomorrow. that will relate to the concept of superficial velocity that accounts for some of the basic process. Other questions? So yeah, I didn't want to make it sound like this is perfect. It's not, and that's why I wanted to re-highlight the fact that you would need to correct that further. Other questions? Okay, so once we've so yeah, we're talking about the closure at the level of the single particle statistics. So our NDF tells us whether we have a particle with velocity UP and volume VP at position X at time T. That's all it tells us. If you want to deal with collisions, that's not what you want. What you need to know is whether you have a pair of particles at that point. So alternatively, what you need to know is whether, if you're sitting at a given position at a given time with a certain velocity, whether there's a particle sufficiently close from you coming towards you. Well, this, we didn't account for that. When we wrote our NDF, we kind of gave that up already. In the Lagrangian framework, we would have this information because we're actually solving and following all those particles. So we actually know, if we want to know whether we have a neighbor coming to us, well, we can figure this out. So we have the multi-particle distribution function, if you will. But in the Eulerian model, it is very unwieldy, so we've given that up right away. So I'll tell you a bit how people have modeled that, but we'll spend very little time on this. I'll just say Lagrangian. Oh. The Lagrangian approach, as well as the microscopic, i.e. particle resolved DNS. We know we know whether we have a particle next to us coming towards us. So positions and velocities are known. Therefore, we can extract what we would call, I would say, the multi-particle distribution function. So not just the simple NDF, but the NDF for as many particles as you want. So you know, given the presence of one particle, whether you have another particle or not. In this Eulerian approach that we've discussed, you solve for f, so let me just say you solve for f sub p, which is the one particle velocity distribution function or number density function. So there's no information on pairs or particle-particle correlations. So if we had this information, we could do a lot. We could, in fact, completely close the collision problem a priori. So the collision, what we wrote on the previous page, you would express in terms of some coefficient that accounts for the cross-sectional area of the particle, so basically the shape that they have and the volume they occupy, that will define whether they can or cannot hit one another. And then you would need to know something about the joint probability of or let's say the probability of finding a particle with a certain characteristic, given the fact that you have another particle with the same characteristic locally. So you would say, essentially, you would need to integrate over all possible volumes, and then you would have some sort of a coefficient that accounts for the overlap between the two volumes of particle 1 and particle 2, and then you will need some information about whether or not you have, whether the two particles are going to be hitting one another. That's unfortunate. So this is classically how this would be written. The important aspect here, so this is a coefficient that tells you something about cross-sectional information for our two particles. So defining the areas that they occupy as they move. But the more important thing here for us is this B. What this B is effectively a coefficient that comes out of the integration of the pair distribution function. So let me write this out explicitly, and then we'll talk about how one could hope to model this if you only have access to the NDF. So this would be the integral, or would be essentially obtained, there's a number of things contained here, from integrating the pair distribution function, which is the next level from the NDF. The NDF is the probability of finding one particle and a certain particle with certain volume, certain velocity, at a certain position. Now we'll be looking for a pair of particles at a certain position, at a certain time t, certain position x. First particle being of size Vp and of velocity up. Second particle being of size Vp star and of velocity up star. I'm passing a lot of details here, but the important thing that I'm saying is this is your pair distribution function. Something that we do not have in our representation. So people have modeled that for a number of years. There's a number of approaches that have been used to try to recover or estimate pairwise information regarding the particles from the NDF. The first contribution along those lines comes from Boltzmann, in fact, and what he proposed was is a reasonably applicable approach in a situation where you have a very dilute flow. And basically his approach was to say that if you assume that in your pair of particles, particle 1 and particle 2 are fully uncorrelated, then a good estimate for the pair distribution function is just essentially to square your number density function. So Boltzmann, back in 1872, proposed for very dilute flows the simple approach where this pairwise distribution function for the particle P and the particle P star, you could write simply as, you could approximate as the product of our NDF, f sub p, at Tx for particle Vp with velocity up, times the same NDF at the same position for particle Vp star velocity up star. So that's essentially throwing out the door all type of particle correlation. So we're saying that all particles evolve independently of one another. And I wanted to close the loop with something we said this morning. If you have a moderately dilute flow, you cannot assume that the behavior of one particle is independent from the behavior of the neighboring particles. So you'll have to have a better model. And for that, there is an opportunity for us to reintroduce the concept of the radial distribution function. And this is, in fact, where this comes from initially. You can model this F2 as being essentially this F2 as provided by Boltzmann. And then correct it. How would you correct it? You would correct it by the use, directly by multiplying by the radial distribution function G of R. That is just the number of pairs that exist at a given position at a given time, separated by the distance R. Okay, so that essentially accounts for the fact that you have, you don't have an equal probability of finding particles separated at R, then at R1, then at R2. This is the number of pairs separated by R. Okay. So one big difference here already that hopefully is clear between Lagrangian and Eulerian methods. Both of them will typically rely on the drag model in order to couple the phases. Okay? In that sense, they will both typically be at best a mesoscopic type of representation, but the collisions have to be modeled in the context of Eulerian methods, while collisions can be handled in a near exact way in the context of a Lagrangian method. So I would argue that here there's a significant pragmatic advantage in the form of the for the Lagrangian method, because you know already whether you have or you know everything about the multi-particle distribution. The problem, though, is that the Eulerian method is dealing with the full statistical problems. Basically, it tells you, or it's a method that we've derived here without any assumption regarding separation of length scales. Again, back to what we were talking about this morning. We have a probabilistic approach in the Eulerian method. In the Lagrangian method, it is way more natural to just actually follow real particles. And then if you have a region where you simply do not have particles, you have no statistical information about that region. You do not know whether the absence of particles is an indication that you cannot have particles in that region, or just an indication that your current sample that you're computing did not give you a particle in that region, and therefore you just don't have data. So basically, the Eulerian method is going to be able to tell you something about the very unlikely, the regions where it's going to be very unlikely for particles to exist, while the Lagrangian method will not. If it is unlikely for a particle to go to a certain region of your computational space, the Lagrangian method will not be able to provide you with statistics on that. So that's the trade-off. Statistical convergence of Lagrangian methods is a challenge. It is less so a challenge for Eulerian methods. Collisions for Eulerian methods is a challenge. It is less so a challenge for Lagrangian methods. Any questions on those ideas? Okay, so let me just formulate now a set of equations that we'll then implement. So we'll take the simplest form of our Williams-Boltzmann spray equation, aka a kinetic equation, not applied to physical gas dynamics, but applied to particles. If I just allow for transport in physical space, and transport in velocity space, Let us include, so we have an FP here. There we go. And that's equal to 0. Okay, so this is my simplified high-dimensional equation that account only for the evolution, for drag, essentially. Now, I can extract moments of this equation in the same way that we extracted moment from the NDF. We can extract moment from the equation verified by the NDF. So the 0th order moment equation will be a dn dt. So this is just integrating all this over all possible velocities. So over all possible x, y, and z velocity for the particle. That's it. Triple integral over this. And what you get is this equation. That's simple enough. That looks a lot like continuity. That tells me that the number density is a conserved quantity that evolves where the particles evolve, or the number density is moved around at the velocity of the particle. Okay? If I take my first order moment in velocity, and I'll say plus assumptions, and we'll talk a bit more about that in a second, then I can easily obtain the following equation. du p dt plus up dot grad up is equal to 1 over tau p uf minus up. Now that equation looks a lot like the Euler equation, except it doesn't have pressure. It's like a pressureless momentum equation, or Euler momentum equation. That tells me that the velocity responds to its own convection, and that velocity responds to drag, essentially. The interesting thing from this pair of equations, if I decide to solve that, is that it is a hydrodynamic-like system of equation. Okay, this looks like fluid equations. It looks a lot like a mass and momentum, fluid mass, fluid momentum conservation equation. Why does it matter? Well, it matters because often you see this being postulated. People will say, well, let's consider the particle phase as a fluid, an interpenetrating fluid that is allowed to penetrate inside the surrounding carrier phase. And so we'll write the following equations. Well, we didn't need to postulate anything here. We derived that from the statistical understanding of what our particle field looks like. So essentially, the first two lowest order moments of your equation give you a hydrodynamic model. There's going to be a number of issues here. One important issue is that there is no pressure in this equation. So it's a pressureless problem. And as a result, this is a system that can lead to the formation of shocks. So basically, we're saying that instabilities should exist in a system like that. We'll go back to that in a second. I want to, let me see, can I? Let me add a page quickly right here. Oh, can I not add a page? Media, okay. I'll write this down there. Well, okay, let me structure that a bit differently. Well, what is the assumption I made here? In order for this to work like this, you need to essentially assume that all the particles at a given place at a given time share the same velocity up. So you have to assume what we would call a monokinetic representation, so a single velocity for all the particles that share the same location. This way you get this model. If you don't make this assumption and stay true to this idea that you can have a full distribution of particle velocity of particle velocities at a given place at a given time, then your moment equations will look a little bit different. And that's what I wanted to show down there. It is possible to solve for those moments and observe the and write that in a more systematic way. So if I rewrite this for shortness of notation as the first order moment being m0, okay, and then I'm going to write as a vector my first order moment as vector m1, which is going to be my, where did I write this? My mean velocities. I think I had this as an uppercase. And I'm going to continue and go to the next order of moments in velocity. So essentially I'm going to write now a second order tensor, m2, which will be the integral over r cubed. So all possible velocities of the dyadic product of the velocity with itself times fp dup. Okay, that's the next step up in order of closure. But if you do that, you can see that in fact it's a very systematic process. The equation you get for m0 is exactly the same one as the one we wrote before. You have an evolution equation for m0 I'm sorry, there should be an n here. That looks like, oops, that looks like this. This is your equation for m0. This is exactly the same equation as the one we wrote before. dn dt plus divergence of particle velocity times n is equal to 0. So the zeroth order equation contains a divergence of the the zeroth order moment equation contains a divergence of the first order moment. We go to the next equation and we find that the first moment equation will contain a divergence. I keep mixing notation. Let me stick to index notation. This will be I, this will be j, and this will be 2. We will have now a divergence of the second order moment. So if you solve for the first order moment evolution, you'll find a divergence of the second order moment showing up. And then we still have our drag term like we wrote before. A drag term looking like this, minus m1i. Okay. So this is just the row story here. First order, zeroth order moment, first order moment. What I wrote on the previous page is not that. What I wrote is up.grad up. up.grad up, what I should really have the divergence of the integral over all possible velocities of up dyadic up times fp dup. So what we're essentially saying is we're assuming, on the previous page, we were assuming that we have a single velocity, in which case you can rewrite this like that. But in a general sense, what you should deal with is every time you write an equation for a moment of order n, you would see the divergence of the moment of n plus 1 show up in your equation. Moment of order 1, divergence of moment of order 2. So now we can continue and do that for the moment of order 3 if we want. It becomes more tedious to write, but not enormously so. So dm ij 2 dt, and as you would expect, this will contain the divergence of the moment of order 3, which will be the integral of all possible velocities of u times f. Drag will play a role here. But it becomes significantly more tedious. And this is wrong, this should be an I. Anyway, we can continue as long as we want, but you can see inherently here the problem that is tied to this idea of solving not for the full f, but for moments of that f. And the problem is you cannot ever hope to close this. This is by definition a non-closed problem, because as soon as you decide to truncate the moment, let's say you want to stop at that equation, then in fact you're going to miss the second order moment. If you say, fine, I need the second order moment, so I'm going to solve an equation for the second order moment, this tells you that you still need to solve an equation for the third order moment. So essentially, until you've solved for all the moments, basically until you've solved for the full f of p, you're going to have to deal with some sort of modeling. So the argument here is that, yes, the Eulerian method inherently, so it has this defect of not being able to deal with collisions readily, but it gives you the full statistical representation of the particle phase. But it does so at one cost, which is an enormous cost. The fact that you have to solve a problem in time, space, and velocity space. If you want to move away from this cost and restrict the problem to just a few equations and make it therefore tractable, you kind of have to give up at least some of your accuracy and re-inject some sort of a model. So basically say that you want to stop here, and the question becomes, how do you represent that? Well, probably the simplest way of representing this second order moment is to go back to what we were doing on the previous page, which is to say, well, if we assume that all the particles that share a position at a given time have the same velocity, then this is my second order moment, my divergence of the second order moment, and therefore everything's fine. But this is an approximation. The real story would require the full knowledge of this. There's a whole lot of different approaches that allow you to deal with this. In particular, what you can do is decide to solve a certain set of moments. Once you have a good enough number of moments, what you can do is reconstruct your full f of p. So from the knowledge of the moments of the distribution, you can estimate what the distribution function should be. And from that estimation of the distribution function, you can extract higher order moments. So this takes us into what's called quadrature-based moment methods. So the question here would be how to close M3. Well, so this is a so-called moment closure problem. And I would direct you, if you're interested in the topic of quadrature-based moment methods. There's a number of people actively working on that, but probably the biggest name right now is Rodney Fox. The second document that you have in your course pack for this afternoon is a paper where we do exactly that. So we take those equations, we solve the M0 and M1, so therefore we solve the mass and momentum of the particle phase. We solve some information about the energy of the particle phase, but then we use a so-called quadrature-based method of moment in order to estimate what the third-order terms look like, and we re-inject them in our equations, and that gives us a complete closed set of equations that we can solve. Why does it matter? Well, it matters for a very important reason, which is that the distribution of particle velocities at a given point is conceptually something that's very critical to the dynamics of particle flows. If I send one particle along that trajectory and another particle along that trajectory, it's very likely that they will not see one another and they will just cross trajectories. That means that at an infinitesimal location that contains both particles, my mean velocity of my particle phase could be just vertical up, but truly it would be formed by one particle going from bottom left to top right and one particle going from bottom right to top left. Those particles don't know anything about one another. They are completely independent, and as a result, the mean velocity locally, this velocity would just be the average between the two velocities. It's mostly a meaningless concept. Yet, if you close your equation at the level of a mean velocity here, therefore if you go back right here, you inherently make the assumption that this is the relevant velocity for us to work with. So if you work with this stuff here, you are making use of this concept of a particle velocity up at a given time at a given space, at a given place in your system. That's all fine and good, but this is a concept that's very problematic. If you force all your particles to have the same velocity at a given place at a given time, that means that there's a lot of things that you're not going to be able to deal with. In particular, you're not going to be able to have interpenetrating streams of particles. Well, that turns out to be a critical characteristic of particle-laden flows, the fact that particles can cross trajectory without seeing one another. When we do fluid mechanics, when we go from the Boltzmann equations and derive from that the Navier-Stokes equations, we make the same assumption. This is the same exact process that allows us to write the Navier-Stokes equation in that form, right? At least the left-hand side in that form. But that's fine because we assume that we have a highly collisional molecular flows, that the molecules are bouncing off one another all the time. Okay? So essentially the assumption is that there's none of that interpenetration. So the issue though is if you don't have collisions, if you don't have molecular collisions, what's happening? Well, really you're looking at a rarefied gas. Okay? You're all the way up in the higher atmosphere or things like that. In that situation, we all know that Navier-Stokes is not valid anymore. Well, if you make use of a Eulerian model of that form, you're basically presuming that something like a Navier-Stokes type closure is appropriate, even though your particle-laden flow is likely to be a rarefied gas problem. Okay? So I'll show you concretely. So we'll build an example that can make this fail grammatically. I have another example here, but we don't need to. I'll show you very concretely in what sense it fails. I don't want to just be negative regarding Euler-Euler methods. Certainly, the more high-order terms you include, the better the model will behave. So if you solve for this, this, and this, now you have some allowance for particles to cross one another. Why? Because now you're basically allowing for particle velocity variance to exist. So at a given point, you have a distribution of velocity that has that is non-zero. And so the higher you, the more you push your closure to high order, the better you're going to be. Okay, there's one more thing I want to do is this to try to give you a positive outlook on Euler methods, and just to close the loop with what we talked about this morning regarding preferential concentration. So now we have a nice little set of equations. We're even going to go back to the simpler set of equations right here, and we'll show how much it contains already regarding preferential concentration. For that, I will get a new page going. There we go. But it's going to be brief, and then we'll start playing with the code for the day. So this is just a quick note on preferential concentration. So if my UF is my fluid velocity and my UP is my particle velocity, then we'll start by making a fairly simple approximation. We'll linearize, we'll take our Newton's second law for the particle, which depends just on drag. We'll assume a short enough response time for the particle, and we'll perform a linearization. I'm not going to go through the details. It's a very simple thing to do. So basically, we're going to say, under the assumption that the Stokes number is low enough, but non-zero, then we would expect the particle velocity to follow fairly closely the fluid velocity. Well, we can do that by simply injecting Navier-Stokes into our Newton's second law and linearizing all this. And the outcome is just this. So in the limit of low Stokes number, so low but larger than 0, we can write that UP can be linearized to UF minus tau P times the acceleration of the fluid, which is just dUF dt plus UF dot grad UF. And that's a first order estimate, that's a linearized estimate in terms of the time scale, so that's plus tau P, plus an change in the order of tau P squared. This is written dimensionally. If I want to write that, if I want to non-dimensionalize by my time scale, it works the same way. I can write that UP is equal to UF minus the Stokes number times dUF dt plus an error of order Stokes squared. This observation was made surprisingly recently by Ferry and Barachender back in 2001. This observation is very practical because even though it is linearizing the effect of Stokes number, so it's assuming a small Stokes, it still allows us to identify the mechanism of preferential concentration. So what is preferential concentration? It is the change of local concentration due to the characteristics of the flow field. What would lead to the change of local concentration in particles? Well, we just wrote our equation for the number density. It is dN dt plus divergence of n times UP is equal to 0. Okay, like a continuity equation written for the particle velocity. Well, in that situation, we know exactly what leads to a change in local n. It is the presence of dilatation or divergence in the field UP. Okay, if the velocity field for the particle phase is not solenoidal, we would expect accumulation or depletion of particles in our domain. So I'll argue here that if we want to know the preferential concentration, it is contained in the divergence of UP. That's all we need to know. And again, why? Well, because we just wrote that dN dt plus divergence of n times UP is equal to 0. So now we can just compute this. What is the divergence of UP? Well, we just wrote an expansion for UP for low Stokes. We can do the math. It is going to give us minus the Stokes number times the divergence of U double contracted, of UF double contracted, what did I say? Minus the Stokes times the gradient of UF double contracted with the gradient of UF. We can rewrite that conveniently as minus the Stokes times S squared minus R squared, where S squared is the double contraction of my strain rate tensor for the fluid. So where S is 1/2 of the symmetric part of the fluid velocity gradient tensor. And R squared is the double contraction of the R antisymmetric tensor, which is then the rotation rate tensor, the antisymmetric part of the fluid velocity gradient tensor. Okay, so that takes us back to undergraduate fluid mechanics and in particular kinematics. If I want to know something about the local characteristics of the flow field, I might be interested in looking at the rate of straining of my flow, the rate of rotation of my flow. While if I'm looking at the double contraction of the velocity gradient tensor, which is what comes out of just taking the divergence of that, what I get is that I just have to look at the difference between the double contraction of the strain rate and the double contraction of the rotation rate. The double contraction of the strain rate will be important in regions of strain. The double contraction of the rotation rate will be important in regions of high vorticity. So now that closes the loop with what we were talking about before. If I place myself in a region with high vorticity and low strain, then R squared will be large, S squared will be small. So if I have high local vorticity and low local strain, then S squared minus R squared will be negative. And as a result, my divergence of my particle phase velocity will be positive. If the divergence of that velocity vector is positive, that means that particle volume is rushing out, meaning that my n locally is going down. My number density is becoming depleted. So high vorticity, low strain means particles getting ejected and the number density going down. So this leads to depletion. The converse is true as well. Low local vorticity, high local strain will give us the exact opposite situation. S squared minus R squared will be larger than 0, which will mean that the divergence of my particle velocity will be less than 0, which means that particle volume will be rushing into my system, meaning I will see accumulation of particles. So this analysis has been conducted, the details of this analysis was conducted first by Maxey, and I think I mentioned that before. That's from Maxey in 1987. But the main point here is that even at the lowest level of closure, so even at the basic hydrodynamic level of closure of the particle dynamics, okay, using an equation for mass and an equation for momentum of the particle phase, we should be able to predict preferential concentration. So something like preferential concentration is a fairly low-hanging fruit, and Euler methods should be doing a good job there. Situations where the flow is more dilute and where particle trajectory can take place, this is going to be a more challenging situation for Eulerian methods. So the upshot here is that Euler, well, let me write fully Euler methods. They can capture preferential concentration. So it's not all bad. but in a sense, you're trading. Again, Eulerian methods will force you to deal with statistical closure questions, while Lagrangian methods force you to deal with a large collection of Lagrangian points, which is a pain to deal with. Eulerian methods, you'll see, will implement that in 2 seconds. Okay, so this is, I guess, a long preamble to what we're going to do today. We're not going to do too much in the second part here. Our tutorial will be in 2 parts. The first one will be to take our Lagrangian method from, well, the day before yesterday, and simplify it down to a situation where we're going to be able to show the failure of the Eulerian method. So what we're going to do is just take our one-way coupled Lagrangian code from, again, from last time. We're going to look at a simpler configuration where we're going to inject particles from the left of our domain, and we're going to inject them at an angle. So 2 streams of particles thrown towards one another, okay? So it's going to be a very simple configuration, and in fact, to make it even simpler, we're not even going to worry about the fluid phase. It will save us some time. So what we're going to do is we're going to go in the code and comment out the fluid solver. So the fluid predictor and the fluid corrector. So basically the velocity solver and the pressure solver, we're going to get rid of that. So assuming a constant 0 velocity fluid, we'll just look at the trajectory of those Lagrangian particles. So that will lead to a small modification of the code. We'll run that. We'll make sure things make sense. And then we'll do the same thing with the Eulerian model. The Eulerian model will be the one that, well, the one we just talked about with a single mean particle velocity. So we'll have an equation for number density and 1 momentum equation, I guess in 2D, 2 momentum equations for the local mean particle velocity. Okay? And we'll solve the same problem with that. Any questions as I transition here to, yep?
What is this difference in the Eulerian, what you have discussed with closure models and the population values?
Well, so this is very much the same type of idea. So I think that there's not a lot of differences between those concepts.
One equation which I saw is Williams equation.
Yeah.
That is population balance equation.
Yes, yes. So, but that's.
I mean, why do we use these closure models rather than directly solving the Eulerian frame of equations for droplet phase as well as for the continuous phase?
Why do we use? Tell me again. So
here we are proposing these closure models, right? And in the full Eulerian multi-phase simulations, where we have the Eulerian equations for continuous phase, I mean the carrier phase, as well as the particle phase or the droplet phase.
Mm-hmm.
So introducing the volume fraction.
But that's how do you get Eulerian equations for the particle phase?
Assuming the particulate continuous.
So the point that I'm trying to make is that this doesn't really exist. You can assume anything you want, but the correct approach is to derive it from the low order moments of a Williams equation. That's essentially the argument I'm trying to make. You can, this is the only proper mathematical way that you can get to a PDE for the particles. There's no, short of just postulating a random equation, there's just no way you can get, there's no way you can obtain those continuum equations for the particles. So all we did here was go through those steps. So we started from the Williams-Spray equation, so basically the Williams-Boltzmann equation or an equivalent Boltzmann equation for the particle phase, and we showed that the low order moments of it give us a continuum equation that we can now solve for number density and particle velocity, and more potentially. So to your question, I think really the low order moments of a population balance approach boils down to a simple Eulerian continuum approach for particles. Those are the same things. I think it's important to know that one derives from the other, and you cannot just say, hey, let's use a Eulerian representation without knowing where it comes from, or else you're going to be missing specifically some of those things we were talking about. The fact that you cannot write a Navier-Stokes-like equation, the convection of particle momentum. if you just postulate your equation, you can feel that this is pretty correct. Well, we'll do an example here that will show you how wrong it is. And the reason why it's wrong is because we're missing higher order moment closures. Okay, so it's important to keep that in mind, I think. Other questions? Yes?
So in the system, before calculating this number of density, we know already this particle velocity. Or don't we?
When we're calculating this?
Yeah. For the system, we know this UP.
Well, the idea is we would solve simultaneously for n and up. So in a representation like this, if I go back, here, this would be the system of continuum equations that we will solve in the Eulerian phase for the particles. We're solving for n and up simultaneously. Does that make sense? Those are coupled equations. Right? This equation depends on up, and this equation, well, the way it's written here doesn't depend on n, but you would need to solve. So I guess one way you could do that is solve for up first, and then from the knowledge of up, solve for n.
I was confused why we are relating the divergence of particle velocity to get fluid velocity. Like, we know particle velocity, then we can directly calculate that divergence.
Oh, okay, yes, I agree with that. But the point here was to try to understand the local flow characteristics that will lead to depletion and accumulation of particles. So I agree that, yes, if you've obtained UP already, you can take the divergence of it, and that will tell you everything about what's happening. What we've obtained here is, as a function of the local fluid phase kinematics, a statement regarding whether we'll be accumulating N or depleting N. Right? This is what we've done. We're saying something about not the particle phase velocity, but regarding the fluid phase velocity. So depending on what the local fluid phase looks like, we can say something about the response of the particles, which is a bit more powerful and allows us to connect to what we saw this morning. So the regions of depletion were regions where vortices were ejecting particles out, and this is this is essentially the kinematic confirmation of this. Okay. Other questions? All right. So let me plug this in. Yeah.
Then does that mean that we don't require a pressure gradient term at all in this particle equation?
So
Because we have not ended up with the pressure gradient.
yeah, so the level at which we've discussed this, we don't have a pressure gradient, but there's additional terms that might lead to a pressure gradient. If we had a collision, we would end up with a behavior that would be very similar to a pressure gradient.
For this formulation, if you want to add E operation kind of automation, then what modeling is required for that?
If you want to add what?
Automation, I mean the droplet
Oh.
Yeah, and the E operation.
Well, that's a loaded question. A lot of things would be required. So this is a representation of an ensemble of particles dispersed already. So what could be added is a process of fragmentation. So you could say that at a certain rate, depending on the local conditions, there is a certain probability that a particle would split into multiple particles. right? Then you would have, this would be one of the terms on the right, this big C term that contain essentially all those interparticle effects. So that could look like a sink term at a certain size and a source term at other sizes based on the different, tied to a process, a fragmentation rate essentially. So you could do that. If you were to do evaporation, this was this G term. So this would be transport in volume space. The issue is, how do you model this? Well, now we're looking at the full distribution in volume space. This is difficult to deal with in a general sense. So you could, the same way as we've discussed before, you could deal with moments of that. Okay? Or alternatively, there's a maybe more brute force approach that's been used with a decent amount of success and that you typically find in commercial codes. That is to take an entire distribution of sizes and discretize it. Brute force create bins. That's called sectional methods. So essentially you would solve what we wrote, but for classes of particles going from size 1 to size 2, and then from size 2 to size 3, and then size 3 to size 4. So the cost would go down as you increase the number of particle size classes. But, and then you would have exchange terms within those different classes of particles. So that's called sectional methods. That's typically what you would find in codes like Fluent or those type of solvers. People like Fox and others are typically looking more at method of moments for this. So how to deal with this problem from the perspective of solving for high order moments in volume space. And there's a lot of work that's being done in hybridizing those approaches. So if instead of having multiple moments, instead if you had like 3 or 4 bins, but then for each of these bins you had a couple of moments, then you could potentially have a pretty decent representation of the distribution of sizes. And then, so this is, it's difficult to talk about in general because the research that's done nowadays is very strongly dependent on the type of problem. For example, people doing soot, they know something about the size distribution. It tends to look like a log normal on one side, so a peak followed by a log normal. So it has this highly bimodal shape, the size distribution of soot particles. And so then it makes sense to assume that the distribution is in fact going to look like a peak and a log normal shape. And if you do that, you can formulate your equations with this assumption and get, if you inject enough physics, you can get something that looks pretty good for pretty low cost. If you want to write a general solver that is agnostic of the physical process, yeah, you would need many bins and the cost is just enormous. 10 bins would mean 10 times the cost. That means, here we're solving number density, velocity, u, v, w. That's 4 equations times, say, 10 bins. That's 40 equations, 40 coupled equations. Wait. Let me see. I will change one quick thing. So while we're talking, you should download the code from, yeah, we've been at it for an hour and 40 minutes already. So we'll download the code for day 3, so the T3 tutorial. There should be 2 directories, I think. One was looking at crossing with Lagrangian particle tracking, and the second one doing the same thing with Eulerian particle tracking. Okay, that should be, there we go. So, I was going to ask you to change those things yourself on your computer, but I don't think it matters too much. It's not particularly exciting. If you go to the first directory, so the one called T3/1_LPT crossing. This directory will contain the code that you looked at last time, and it's one-way coupled form. Okay. So no source term feeding back on the particles. So probably the simplest Lagrangian tracking code that we've looked at. Yeah, the simplest code we've looked at. There's two changes. I'm going to show you the first one. It's just a reduction in cost. We're just going to make our life extremely easy. In this demo flow that F9, is that big enough? Or one more time? One more time or big enough? Okay, so the one change here is the following. If you scroll down a bit, I have, well, no, that's not true. There's a couple of changes I've removed. So this is where I was masking out the cylinder in the middle. I've removed the cylinder altogether. Okay. The fluid is going uniformly from left to right at velocity 1. There's no wall at all in the system. But it's in the main code here, in the main time integration that I've made the change. I'm commenting out the velocity step and the pressure step. Okay? We're simply not even going to solve the Navier-Stokes equation. We'll look at the particles only. So the only thing that we'll do is solve for the particle phase represented as a collection of Lagrangian points. So those two things are commented out, the code will go faster. The second thing is I'm going to change, or I have changed in the code that you're looking at, I have changed the boundary condition at the inflow for the particles. So instead of uniformly injecting them from left to right, you'll see what we're doing. So this is an LPT. I believe that there's only like 3 or 4 lines that have changed. I've reduced the injection rate a little bit because instead of injecting them uniformly everywhere, I will inject the particles from 2 small bands in my domain. And I've reduced their velocity a little bit. So they're going to be coming in at a velocity of 0.5. Units don't really matter here. And at a certain volume flow rate of which the unit doesn't really matter. The important thing is going to be the shape of the injection process. So this was this chunk of code in LPT step, where at each time step we add particles until we've reached a sufficient number of particles. So this is the do while where we keep adding until we've added enough particles. The particles will still be introduced on the very left of the domain. And then I'll draw a random number. Now I'm realizing that I have a bug here. Yeah, I have a bug. Well, fine. So there's a bug. So I'm drawing a random number between 0 and 1. If that random number is above 0.5, then I'll add a particle in the upper stream. If it's below 0.5, I'll go to this else here, and I'll add a particle in the lower stream. The upper stream I'll bound between oh, sorry, the other way around. So if it's above 0.5, I'm putting them in the lower stream. My domain goes from Ly minus Ly over 2 to Ly over 2. I'm centered at 0. So between Ly well, between 40% of Ly. So my domain goes down to minus 0.5 times Ly. A little bit above that, minus 0.4 times Ly. I'll start injecting particles. and I'll do that for 20% of my domain size. So those are the random locations at which I place particles. That's my lower stream. My lower stream is going to be going forward at velocity UPN, which was 0.5, and up in the v direction at velocity UPN. That means that my lower stream of particles is going to go up at 45 degrees. If I draw this number and it's below 0.5, I'll do the same thing, but above, the symmetry above. So basically, I'll be looking at, yeah, that's where, that doesn't look that symmetric, does it? 0.4 then times 2. We'll see if it doesn't look symmetric. It doesn't matter. Basically, I'm creating another band of particles above, and this time they're going to be injected at an angle 45 degrees down. So they'll be coming in at velocity UP from left to right, but minus UP. Okay, so I'll have a stream of particle going up, a stream of particle going down. That's it. No other change in the code from these two things. So we're running without flow solver. We're not worrying about the induced flow field. So what should happen? Can you make predictions regarding what should be the behavior of this simulation? Stream of particle, up and down. It does depend on tau p, yes. Oh, I guess I should go back because did I change tau p? Tau p is some value, 10. So yes, it depends on tau p because I have an underlying flow field and we have drag. This flow field is constant at velocity 1, I think. So if tau p is small, the particles will very rapidly start shooting straight and follow the fluid. If tau p is large, the particle should continue and not really care about the fluid. Well, here the Stokes number, so the height of this domain is 1 and the velocity is 1, the characteristic fluid timescale is 1. Tau p is 10, that means my Stokes number is 10. So the particles are going to be fairly little affected by the fluid. It's going to take them a while for their trajectories to bend to the fluid, the expected fluid trajectory. Okay? Now, since I have a stream coming up and a stream coming down, they will intersect. What will happen there? There is no collision. They will pass through. They will not see one another in any way. So let's check. Hopefully this runs without any problem. It should run very fast. So those are the particles. I can color them by the, say, the y velocity. I can make them large enough to be visible. But there you go. No surprise here. Now, this is simple in the Lagrangian setting. But where it's going to become tricky for the Eulerian approach is if you look here in this diamond-shaped region, my Lagrangian model predicts a multi-valued particle velocity. That means I'm equally likely, like literally equally likely, if I pick randomly a particle inside that diamond shape here, I'm equally likely to find it with either positive vertical velocity or negative vertical velocity. Literally, if I were to plot the distribution function of vertical velocities for my particles in this region, you would see two peaks. It's literally bimodal distribution. The Eulerian method that we looked at, the hydrodynamic-like Eulerian method that is closed at the level of the first order moment, is only working with the concept of a mean particle velocity. What it means is that at any point, I'm assuming that I have a single velocity. That doesn't seem unreasonable. In fact, all along here and up to here, this is a completely reasonable way of writing my equations. But in that region, there's going to be a major issue. Because in that region, I'm not going to be able to represent the fact that the velocity distribution is bimodal. So if we take our Eulerian equations and implement them, what would you predict would happen here? It will average, yes. Which means what? Single stream, yeah. So we'll see that this is in fact going to happen. So before we do that, we'll take a look at the Eulerian model. The Eulerian model is done on the code that I just showed. So essentially the code that we had, we're going to remove the LPT from it. And we're going to add a new file instead that I've called EPT for Eulerian particle tracking. The flow solver is still not used. There's no change anywhere in the code except for that EPT file. So we really only need to look at the, that's not true. Of course, I've also changed the output. So now I need to add more inside outputs since I'm not going to have point particles to output, but I'm going to have Eulerian fields for the particle phase. So let's look at that quickly. I'll walk you through the approach that I've used to discretize the Eulerian equation. You'll notice, by the way, the Eulerian equations we derived, they don't have viscosity, they don't have pressure. They're fundamentally hyperbolic equations. Those hyperbolic equations will require transport methods, transport schemes that are capable of dealing with shocks. Right? We're talking about methods here that there's no stabilization. Centered scheme will not be able to handle those equations. So we need to have fundamentally hyperbolic methods, by which I mean ENO type schemes, WENO type schemes, upwinded type schemes, muscle type schemes. So if you've worked in hyperbolic, basic incompressible flows and discretizations of, for the Euler equations, this is the type of schemes that we need to use. Without that, we can't solve those equations. An ENO or WENO would be pretty tedious. We'll get to a WENO because we're not going to be able to avoid that next week. But for now, we're going to stick to the simplest possible implementation. We'll do pure upwinded transport. Okay, so pure upwinding. I'm going to look at the sign of the velocities. The velocity goes from left to right. I'll upwind by taking information from the left. If the velocity goes from right to left, I'll upwind by taking information from the right. That's the scheme I'm going to write. Okay. Okay, so let's move to the second directory. Thank you.
Do you eat anything?
Oh, no, I'm good. Thank you.
Tea?
No, water is fine. Thanks. So quickly, I'll show you. I keep forgetting. So in terms of visualization, I will add a few variables. Nothing too exciting, but I'm going to create two new directories for visualization. One will be called volfrac for volume fraction. So I'm not going to output directly the number density. I'm going to express everything in terms. Number density and volume fraction are equivalent, provided that the particle size is constant. Okay, so here I'm going to be working with a particle volume fraction instead of a number density. But again, it's just a constant coefficient that multiplies everything. And then I'm going to have the mean particle velocity that I'm going to call pod_vel. The code to write it is very boring. There's nothing specific here. This is those two chunks here. Nothing useful. Let me close this. And now we're going to go to the more important part, which is the way this EPT code looks like, the way it looks. Okay. In the previous exercise, we had only a tau p is equal to 10. I hard-coded it. So we'll do the same thing here. Single tau p, it doesn't matter. We have some combination of diameters, viscosity, and densities leading to a characteristic timescale 10 times that of the fluid. We need an array to store our volume fraction. That's going to be this. I could, again, equally have done the same thing with number density. And I need a place to store my mean particle velocity, UP and VP. The product of the two will give me what I'm calling here the particle momentum. The units are not right. It's missing a density multiplication by the density, but conceptually, it's the product of some measure of the number of particles times the velocity of those particles. So it's a measure of the amount of momentum that I have locally in my particle phase. So this will be my zeroth order moment of my number density function. These two will be the two first order moments of my number density function. Okay? The evolution of this depends on the divergence of this. The evolution of this depends on the divergence of the second order moments that I'm going to replace by an assumption that my velocity is unique. This is my initialization for the Eulerian particle tracking stuff. I'm initializing, not that it really matters, but I'm initializing my volume fraction at 0, my full velocity at 1 in x and 0 in v. I'm not sure why I'm doing that, I don't remember, but this doesn't matter, we're going to override this. What matters is the inlet boundary condition for my problem. I want here to mimic what was done in the Lagrangian particle injection. So on the left, I don't need to draw random numbers because I know exactly the regions where stuff was coming in from the Lagrangian code. So I'm going to look at this region here. So I have those two regions contained between 0.2 times Ly and 0.4 times Ly, or minus that. I'm going to deal with both of them simultaneously by putting an absolute value for y. If I'm lying between this within those regions, I'm going to set my volume fraction to some constant number. It doesn't matter, again, it's not coupled. So how many particles I have is irrelevant to the physics of the problem. So I'm not going to worry about what my volume fraction should be in the same way that we haven't worried about that for the Lagrangian representation. So my volume fraction is going to be non-zero. My horizontal velocity is going to be 0.5, like in the Lagrangian code. And then if I'm on the upper portion of my domain, I'm going to be injecting with a vertical velocity down. If I'm on the lower portion, I'm going to be injecting with a vertical velocity up. So this is just a boundary condition saying those two regions have a non-zero concentration, and velocity here is like this, and here it's like this. Okay? Now, from the knowledge of the velocity and the volume fraction, I can take the product of the two, and that gives me the momentum for my particle phase in x and in y. Okay? Now, here comes the very simple. Well, it doesn't look that simple like this. It is not supposed to look that bad. Let me try to convince you of that. You see, if you make it smaller, it looks a lot more easy to digest. The symmetry here might make it a bit easier to work with. So I'll tell you about what the different chunks are, then we'll zoom in a bit more. I need to compute essentially two things. If we go, well, I'm not going to unplug and go back. Well, do I need to? No, I don't need to unplug. This is the equations we're solving, right? So we need to compute this in an upwinded fashion, take the divergence of it, then compute this in an upwinded fashion, and then we'll need to add drag. Okay? We're going to compute this the same way we're going to compute that. For both cases, we're going to do simple upwinding. So that's going to be what most of the long code here was. So it's going to be testing whether the flow is going from left to right or right to left, up to bottom or bottom to up. And then after that, we're going to add this term. So that's all we need to do. And that's how it ends up looking. This is the computation of the convective term. You should be able to read directly on your, so I understand you probably cannot read that, but you should be able to read on your screen. There should be two columns here, essentially. One that contains max of 0, UP statements. And the second column that contains min of 0, UP. What this is the way I'm dealing with upwinding. By taking the max of 0 and UP, I'm basically getting a non-zero value only if UP is more than 0. So if UP is positive, meaning the flow is going from left to right, I'm going to be upwinding by discretizing using information from the left, and that's what I'm doing right after. And then the downwinded part is the min of 0, UP. If UP is negative, the flow is going from this time right to left, and therefore I need to use information shifted in location from the right on my grid. So this is all the upwind, this is all the downwind statements. They are done first for UP and then for VP, UP, VP, UP, VP, UP, VP, UP, etc., etc. And then I have three blocks here. The first block is solving the evolution equation for the number density or volume fraction. The second block is solving for the evolution equation for the x momentum of the particles, and this is the y momentum of the particles. Three blocks, three equations. Those are my upwinded term, my downwinded terms. Okay, so this is all very straightforward and pretty much copy and paste. This is then where I advance the field, so I just add the right-hand side to my equations. That contains everything except for drag. Right before doing that, what I'm going to do is I'm going to recreate my particle velocity. Now that I've advanced my momentum and advanced my volume fraction, I can take my new momentum, divide by my new volume fraction, and it will give me my new particle velocity. There's one little thing that I need to be careful about right here, which is that if my volume fraction is 0, if I don't have any particle, then I can't possibly define appropriately a velocity. So I can't define my momentum, right? If I have 0 momentum, this is all fine. If I have no particle and no momentum, still the ratio of the two is not defined. So I will only divide by volume fraction if that volume fraction is non-zero, it's larger than some small value, say 10 to minus 10. I take that ratio, that gives me my velocity. Otherwise, I'll just keep my field clean and I'll say that my velocity is 0. And that's it. The only thing I need to add to this is the drag. What is the drag? Well, we wrote already what the drag is. It's essentially just dt times the fluid velocity at the cell center. Oh, by the way, I should have said I'm solving those equations here not in the staggered format. Everything is collocated. Okay? I don't have to worry about pressure coupling here, so there's no need for staggering. So volume fraction, x momentum, y momentum, they all live on my cell. That means that to compute drag, I need to interpolate the velocity from the cell faces back to the cell center. So I have 1/2 of velocity to the right plus velocity to the right. Velocity to the left to velocity to the right. Minus my corresponding UP. And I'm going to divide that by my tau P. There we go. This is it. There's nothing else. So you can see how short it is. In terms of implementation effort, typically a basic Eulerian method is going to be significantly simpler than most Lagrangian methods. The other advantage is that this, if I want to put that in a parallel computer, it is very straightforward. I can use simple domain decomposition approaches with OpenMP or MPI. I can make this scale up to thousands of processes very easily. In the Lagrangian code, things are going to be more tricky. Exchanging particles between processors is going to be complicated. Making sure the amount of work, meaning the number of particles, remains more or less the same over many processors can be a challenge. So parallel performance for this will be easier to achieve. Okay, so any questions on this? Yeah.
So in this case, we are basically not dealing with particles exactly like in Lagrangian tracking, and in place of that, we are taking the volume fraction.
Yeah. Yeah. So we're working here with, again, zeros and first order moments of this number density function. So we're not looking at. We're asking ourselves, what is the local, what is, at a given time, at a given point, the probability of finding a particle with a certain velocity? That's essentially what we're saying. But on top of that, we're adding here, because of the level of closure, this assumption that we don't know what the velocity is, but we know that there's only one velocity. Other questions? Okay, so let's run this quickly. Okay, so if we do things correctly, if we have done things correctly, this is what you should see. So probably the most natural thing for us to look at is the volume fraction. Few things to point out. So remember, we're not particularly interested in what the actual value is. It's mostly irrelevant because we don't have any coupling, so I haven't paid too much attention whether the values were meaningful or not. But outside of those two streams, we have no particles. Then we have those two streams where particles are getting injected. You'll notice that this is a pretty highly diffusive solution, right? This should be the correct solution for those streams. Should be sharp. We should essentially have Heaviside-like bands of particles. There should be no numerical diffusion. Well, ideally, there would be no numerical diffusion. There is no reason for us to have regions where basically we should either have no particles or have particles at the concentration that was set by this inflow condition. Anything in between, that comes from numerical diffusion. Why do we see numerical diffusion here? Well, because I just use a first order upwind scheme. There is as much diffusion as essentially it is possible to have in this case. But we will all right, so that's my volume fraction. Does that correspond to what you expected? So what you see is, like we predicted, the streams are not interpenetrating. They cannot be interpenetrating. One interesting consequence of the fact that the streams cannot interpenetrate is that there is no mechanism here for the volume fraction to remain bounded. Really, all the particles are expected to accumulate in the thinnest possible region. In fact, if you were to refine the mesh, you would see that the particles will always end up in a band of thickness 1 cell. Why is that? Well, again, because the particles cannot interpenetrate. You, however, can predict accurately the mean velocity. Indeed, with the stream and that stream of particles, the mean velocity becomes necessarily a velocity going from left to right. With the stream of particles going from left to right, that all accumulate here, well, you end up with essentially your your entire ensemble of particles distributed in the thinnest possible region that your mesh can capture. This, in the realm of hyperbolic transport schemes, is what we call a shock. Okay, our scheme here, not our scheme, our set of equations is prone to forming concentration shocks. Okay, this is not a shock due to the physics of compressible flows. This is a shock due to the fact that we're solving hyperbolic equations without pressure and without interpenetration. And so if you throw two streams at one another, they'll accumulate in a region as thin as you can possibly resolve. So we argued that particle-based methods, so basically Lagrangian methods, will struggle with respect to statistical convergence. Regions where you don't have Lagrangian particles are regions where you will know nothing about the Lagrangian particles that might have existed during other realizations. Okay, so regions where there's only very few particles, you'll have only very poor convergence of the statistics of those few particles. Eulerian methods don't have this problem. A Eulerian method can tell you very confidently where you have particles, where you don't have particles, and it can tell you very confidently also what is the velocity of the particles in regions where there's very, very few particles. So statistical convergence is not a problem. It's inherently a good statistical model. However, mesh convergence now is becoming a problem. What happens if I refine this? Well, I'll see a completely different answer with a peak of concentration. As I keep refining my dy, my mesh my mesh size in y direction, as I keep refining it by factors of 2, my maximum concentration will keep going up by factors of 2. All right, so this under mesh refinement diverges. Lagrangian methods under mesh refinement will converge. It's an important aspect because you find still pretty often people who use those types of equations, of Eulerian equations for particles, and then do mesh refinement studies and conclude that once they have a fine enough mesh, their results are trustworthy, and they make use of this information in order to carry on detailed studies. It's very, very dangerous. Those methods, by definition, cannot converge on the mesh refinement. Basically, their capability of converging on the mesh refinement depends entirely on your capability, if I go back here and scroll back, and your capability of providing a good estimate for this. Well, what we've just shown is that for the simple trajectory crossing problem, this model here, therefore the classic hydrodynamic closure of your transport equations, it is not a good model. This example here was the same thing but done with turbulence. So this is homogeneous isotropic turbulence. I'm putting particles in there. Those little points here, so those are two subsequent times. This is pretty early on, this is later on. This is done with Lagrangian methods. Okay? Here I'm tracking individual points. You can see that because my choice of Stokes number was on the order of 1, I'm getting what's called preferential concentration. We've talked about that. I have regions that get depleted of particles and regions where I accumulate more particles. Next to that, I'm extracting from the Lagrangian simulation, I'm extracting a corresponding volume fraction. So this is now a Eulerian field of volume fraction, but extracted from Lagrangian data. So you can consider these two to be essentially the same. Then what you see on the third column is this model that we've just implemented. What you see is exactly what I illustrated in this little test case. In turbulence, in particular when you have preferential concentration, particles get ejected out of vortices and kind of bounce into another vortex and kind of oscillate back and forth into vortices. An inherent process taking place here is trajectory crossing. If you don't have the support for trajectory crossing, this is what you get. Basically, the same type of shock of infinitesimal thickness regions with all the particles being contained in that will then kind of move around and do their thing, but in a completely meaningless way. If I were to refine that, I would just get thinner strands. If you look at the physics of that, I can tell you that you're not going to get a Nobel Prize. So this is useless. If we go now to this method, where now you say, OK, I need a second order moment. And for that second order moment, I'm going to need a third order moment, but I'll estimate this from the knowledge I have already regarding the zeroth order, first order, and second order moment. So basically, I'll use what's called a quadrature-based moment closure in order to estimate this thing. And this is discussed in the paper that I've added to your course pack. If you do this, now you have some estimation for this that allows for some level of trajectory crossing. Well, if I scroll back up, this is what this volume fraction here represents. So now this is no longer a kinetic model. This is no longer a hydrodynamic model. We're not saying that we have a Navier-Stokes-like behavior. And now what you can see is that the difference between this and that is very small. There's an enormous between this and that. Now trajectory crossing exists. It's possible for those strands of particles to interact and intersect. It's not perfect because our statistical closure is done only at the level of the third order moment, and there's probably way more happening. In particular, in full 3D turbulence, you could imagine that there's particles being thrown at one another from lots of different directions, and you probably would need many moments. So you can still see non-physical shocks, but they're not nearly as bad as what you can see right here. So that points out the kind of this trade-off, really. Lagrangian methods, you'll have a very difficult time saying anything converge from a statistical standpoint about that region because there's no particle there. Okay, so you don't know what to say here. Eulerian methods, they'll allow you to say something under a number of assumptions. Under essentially the assumption that your statistical closure is good enough for the class of problem you're looking at. So in particular, if you have trajectory crossing, moderate Stokes number, you're going to have, Eulerian methods are going to struggle. I'll point out, where am I here? I'll point out one more thing. Well, maybe we can take a quick look at the velocity field. See, this is my velocity magnitude in x and in y. So let's look at the y velocity. What I was saying before is that from a statistical standpoint, there's no difficulty here in accessing velocity information even in regions where you don't have particles. This is my vertical velocity for my upper stream and vertical velocity for my lower stream. You can see again the problem is that we don't allow for those two velocities to coexist in the middle. The reason why we get to this blue, that's not blue, that's very much green. The reason why we jump to this green value, the green value is 0, is because up there the volume fraction is now less than 10 to minus 10. This was this clipping that I had before. So I don't want to keep dividing by smaller and smaller numbers, even though it would probably be fine. So I'm just giving up on trying to predict what the velocity is here. But that means that here my volume fraction is 10 to minus 10. A Lagrangian code will have no clue what the velocity is. If my volume fraction is 10 to minus 10, there's basically, statistically, there's an incredibly low probability that I even have a Lagrangian particle there, and therefore I have no velocity information. All right, any questions on this? If not, I have, I think, only one last point I want to make, and then we'll be essentially done for today. The point that I want to make relates to interactions with walls. So how does everything we've talked about today apply to the question of particles bouncing on a wall? Let me see. Well, we could set it up reasonably quickly, but in fact, the theme for tomorrow will be collisions, so we'll keep that, I think, for tomorrow. But consider the following case. So if you consider the following problem, of a flat wall and particles being thrown onto that flat wall, okay? Let's assume that a particle hitting a wall responds simply by undergoing specular reflection. Okay, no loss of energy, would just bounce with a simple reflection of the wall normal velocity. Okay? So what's going to happen in that situation? So if we put in specular reflection in Lagrangian code, it will just give us specular reflection. Our particles will be coming in and then our particles will be leaving after bouncing, which I'll represent in red. Right? Nothing too surprising here. How will the Eulerian method deal with that? Volume fraction boundary condition? Well, but so what type of boundary condition? So
there has to be some sort of collision rule.
Velocity should take care of that, because now we are talking in terms of volume fraction.
So yeah, we're talking in terms of volume fraction. So if you just disallow for penetration of particles in the wall, then the particle velocity field would have to be responsible for carrying your volume fraction of particles anywhere you want. So you would just have to rely on the fact that you have a zero flux of particles on the wall in order to get reasonable behavior. Okay? So now the question becomes, we don't need to do anything on the volume fraction. Do we need to do anything on the velocity? Yeah, right? Here we're looking at specular reflection, so we need to apply a symmetry condition on the, or I guess a reflection condition Yeah, a symmetry condition on the particle velocity. So our boundary condition would be to apply a Neumann condition on the wall tangent component and flip the sign of the wall normal component, right? A pure symmetry condition on the velocity. So how would that work? What would be the outcome? Is our Eulerian field going to bounce on the wall all nicely? I'm not trying to make this into a trick question, but so yeah, it will be exactly the same as what we just simulated. Look in that region. In that region, I have particles which are incoming and particles which are moving up. This is exactly the same problem as the stream crossing problem we've just done. Whether we decide to simulate only half of it and apply a symmetry condition or simulate the full problem is exactly the same thing. So basically, all along that wall, here's our problem. We need our particles to be both incoming and departing the wall. That means we need inherently to have a multi-velocity representation. We need a polykinetic representation of our particle phase. Okay, so knowing that, what would you expect a Eulerian method would do if you throw a stream of particles at the wall? It would do, oops, can you see this, or let me change color. It would get in there all fine, and then it would just shoot out essentially all straight along the wall. This is what your standard Lagrangian method would give you. Sorry, Eulerian method. So again, you can see that even if you make the argument that your Stokes number or your particle distribution is such that trajectory crossing are not that expected, well, you better hope that there's no interactions with walls or surfaces in any way, or else you'll be in trouble. All right, any questions on this? No, that's not true. There are other ways of dealing with this. You can make an assumption regarding what is the distribution of. So essentially, you have to say something about what the velocity distribution looks like. Okay. Kind of the brute force way is to just solve for the high order moments. So say something concrete about what the distribution looks like. Alternatively, you can just presume something about what the distribution looks like. For example, you could say, well, maybe the distribution would be reasonably approximated with a Gaussian function. If you do that, then if you can say something about the amount of agitation, and in fact you can end up, so it is essentially the same way as going one order, high order moments further. Then you can say, well, now I have this idea about the level of fluctuation in my velocity. I'll just fit a Gaussian distribution to that. And then you'll be able to get rid of this problem. But this is how you're going to get rid of this problem, though. If I assume that I have a Gaussian velocity distribution, then I'll be spreading my stream of particles in a way that looks like this. It's not particularly clear in the way I've sketched that, but the idea is you would predict higher concentration near the wall and lower concentration. Basically, you would say the particles are leaving with this horizontal, wall tangent velocity, but there's a distribution, say a Gaussian distribution around it. Okay, and then upon collision, if you've set up your equations appropriately, you would predict an increase in the local fluctuation of velocity, and therefore you would have a higher spread in your Gaussian distribution, and you would be able to get some spreading behind. So most Eulerian models that are closed at a further level than just first order will give you some sort of a Gaussian distribution upon impact like this. I would argue that this is better than nothing. I can give you one reference, or at least one name of a typical model that people use for this. What am I doing here? If you want to get, if you want to read more on this, I would refer you to the topic of anisotropic Gaussian model. Why anisotropic Gaussian? Well, because you're solving for a 3D flow field, and therefore you probably want to have a Gaussian distribution for the u velocity, for the v velocity, and for the w velocity. And the same way you want to have a Gaussian distribution in x, in y, and z. So you basically have to have some sort of a multi-Gaussian representation, which doesn't have to be the same in all directions. So that gives, you can write this, and you can write a closed form of it. Essentially what you're doing is you're presuming the shape of the velocity distribution. You're saying it's Gaussian. It's characterized by a mean, which we've solved for already. The only additional parameter you need is variance. You can write an equation for it. It would depend on third order moments, but those you can evaluate directly if you presume that your distribution function is a Gaussian. So it is now a closed problem. The issue is that we find that velocity distribution functions for particle systems are very non-Gaussian. So, but it works. You can make it work, and it certainly extends the standard Euler method. Other questions? Yeah.
Both the streams of particles are colliding here and going straight. So what is wrong in it? That's what I'm not getting.
So what is what?
What is wrong in it?
What is wrong? Well, the fact that really a correct solution was the Lagrangian solution. The streams were set up to penetrate.
No, but if the two particles are coming over here and they will collide, right?
Oh, but we don't have collisions. So why would you get a solution that gives you collisions if you haven't modeled collisions? We haven't included collisions. We have no process here that would justify the streams to merge. I agree with you, right? If you had collisions, and particularly if you had some sort of an aggregation process, what the Eulerian solution gives us, it would probably be pretty reasonable. This is not unreasonable in a situation where the particles stick once they collide. But hey, look at the code that we wrote. It contains nothing about collisions. So
Volume fraction automatically will cover that collision, right?
No. Collisions was a right-hand side term in our Williams-Boltzmann equation. The equation we're solving now has no clue what collisions represent. The correct solution would be the interpenetration of the stream. In fact, right, this is a situation where it's trivial to solve this exactly in the Lagrangian frame. Right? Really, the Lagrangian frame gives you a simple method of characteristic solution to the problem. So it is, in fact, an analytical solution. You can solve that back of the envelope, no interaction. So the Lagrangian solution here, well, I guess I'm not showing it, but a Lagrangian solution is the exact solution of the problem. A Eulerian solution should match that. And in fact, if you go to higher moment closures, it will match it. That's what I was trying to show was this, oh, well, again, I'm not on with those turbulence snapshots. That as you close your equations at the higher order moments, you end up matching better and better the Lagrangian solution. All right, any other questions? If not, we'll wrap up for today. Tomorrow we'll be doing, we'll be talking about collisions. I'll give you a reasonably straightforward, well, basically we'll go back to our flow in the cylinder, where we saw particles interpenetrating and all, penetrating inside the cylinder. We'll fix that. I'll walk you through the model. We'll discuss it tomorrow morning first, but then we'll implement it in the afternoon. In the interest of efficiency, I'll just give you the collision model, at least one first implementation of it. And then what we'll do is I'll ask you to think about ways to speed it up. So we'll talk about the cost of this. I'll give you a brute force version that will work. But then I'll ask you to think about how we can make it work more efficiently. Okay? All right, thank you for your attention, and I'll see you tomorrow.